Hi, I'm Dr. Kelly, and I'm presenting my paper, Which Sentence Embeddings and Which Layers Encode Syntactic Structure. This is research that was conducted at the Pennsylvania State University and funded by America's National Science Foundation and Canada's Natural Sciences and Engineering Research Council. For this paper and more of my papers, please visit my ORCID profile. The link can be found in the bottom right corner of the poster. The objective of this research is to explore what types of sentence embeddings are effective at encoding the syntactic structure of English sentences. Embeddings, also known as semantic vectors or distributional semantic models, are computational models that represent the meanings of words or sentences as points in high-dimensional space. Distance between word embeddings captures similarity in meaning. For example, the embeddings for below and above would be located close together in the space, whereas, for example, postage and above would be further apart. Can distance between sentence embeddings capture similarity in syntactic structure? To investigate this question, we used two different data sets. One was a data set of sentences generated by Mechanical Turk workers from partial sentence prompts. These sentences consisted of prepositional object sentences, such as the sailor mailed a letter to his sweetheart, direct object sentences, such as the sailor mailed his sweetheart a letter, and other sentences that are neither prepositional object nor direct object, such as the inventor showed me how it works. We also used sentences sampled from the European Parliamentary Corpus, specifically active voice sentences such as I agree with your analysis, and passive voice sentence such as the analysis has been agreed on. The models that we use include the glove word embeddings, beagle word embeddings, and from one of our other papers, the hierarchical holographic model word embeddings. We also, as a baseline, include random word embeddings created by sampling from Gaussian noise. And we include the BERT neural language model. To construct sentence embeddings using these models, we use a variety of techniques. We sum word embeddings, we permute word embeddings by absolute position in the sentence, we permute word embeddings by relative position in the sentence, we convolve n-grams of the word embeddings, or in the case of the BERT neural language model, we average the hidden states of the model over time. We use two different metrics for measuring the success of the models. One of those metrics is spatial separability, which we measure as sensitivity index, or D prime. The other is classification accuracy, which we measure using generalized linear model regression classifiers. We find that in the case of the BERT neural language model, the hidden layers in the middle of the model are best able to discriminate PO and DO sentences. These layers are the furthest removed for both the input and the output, and thus are the most abstract. Similarly, for separability of DO sentences, we find strong performance for the hierarchical holographic model, which suggests that convolution-based approaches are worth further exploration, and it suggests that more abstract representations better capture syntactic structures. With regard to the PO versus non-PO discrimination, we find that the random embedding baseline is sufficient, and this is because this syntactic distinction is quite trivial. You can detect a PO versus non-PO sentence simply by checking for the location and presence of the function word to. Finally, looking at classification accuracy, we find that BERT has the best overall performance of any of the models, though it's a somewhat unfair comparison as it is trained on a great deal more data. Thanks for listening. If you've got questions, comments, or suggestions, talk to me when I'm at my poster or reach me at m.alex.kelly@bucknell.edu.